Okay, let's just jump right in. MRI machines. You've seen them, maybe you've even been in one. They feel like something straight out of science fiction, right? These machines give us these unbelievably detailed pictures from inside our own bodies, completely changing medicine. And the crazy part? No harmful radiation. So, how in the world does it actually do that?
Oh yeah, if you've ever had an MRI, you know exactly what I'm talking about. That feeling. You're sliding into this tight, narrow tube. Then the noise starts, this incredibly loud banging and clunking. It's a lot. And you're just lying there thinking, what is possibly happening right now?
And that's the big question we're going to tackle today. You see, it's not like an X-ray, which, just shoots radiation through you. And it's not an ultrasound that bounces sound waves around. No, the way an MRI works is, well, it's a whole different ballgame. We're about to take a deep dive into the wild world of quantum physics and some seriously impressive engineering.
All right, so to really get how an MRI works, we've got to shrink way, way down. I'm talking subatomic. We need to look at the single most common atom in your entire body and a really bizarre quantum property that it has.
Yep, it's hydrogen. You are literally made of this stuff. It's in all the water in your body, in your fat cells, everywhere. And what's amazing is that the entire massive, complicated MRI machine is basically designed to do just one simple thing. Have a conversation with the hydrogen atoms inside you and then listen very, very carefully to their reply.
So the key to this whole thing is a quantum property called spin. And right away, let me just say, don't picture a tiny spinning top. It's not really spinning. In the quantum world, spin is just a built-in property that particles have, kind of like mass or electric charge. But here's what you do need to know. For hydrogen, this spin makes every single one of its nuclei behave like a teeny, tiny little bar magnet.
Okay, so check this out. Right now, as you're sitting there, all those little hydrogen bar magnets in your body are pointing every which way. They're a total mess, completely random, so they all just cancel each other out. But the second you slide into that MRI tube, bam, that incredibly powerful magnetic field forces a bunch of them to snap to attention, all pointing in the same direction. And suddenly you go from chaos to order, creating a single magnetic signal that the machine can actually detect.
This is where it gets really cool. It's basically a three-step dance. Step 1, align. The big magnet gets all the hydrogen atoms pointing the same way. Step 2, nudge. The machine blasts them with a quick radio pulse, which is just enough to knock them sideways out of alignment. And then step 3, listen. This is the crucial part. As those atoms naturally wobble back into line, they give off a tiny bit of energy, a faint radio signal. And a receiver coil inside the machine is listening for that exact signal. That little echo, that's everything. It's the raw data for the entire image.
But here's the catch. To get a signal that's strong enough to actually, hear, you need to align those atoms with an absolutely insane amount of magnetic force. And this is where we move from quantum physics to just pure brute force engineering.
So how strong are we talking? Well, a typical MRI you'd find in a hospital operates at about 1.5 to 3 Tesla. Now, Tesla is just the unit for magnetic field strength, and I know those numbers don't mean a whole lot by themselves. So let's put that into perspective for a second. We're talking about a magnetic field that is up to 300,000 times stronger than the Earth's own magnetic field. That is just mind-blowing. It is so powerful that if someone accidentally brought a metal wheelchair into the room, it would become a projectile, flying across the room and slamming into the machine. So yeah, creating a field that strong and keeping it stable, that's a massive, massive engineering problem.
And you can't just build a bigger electromagnet, right? If you tried to pump enough electricity through a normal copper wire to create that kind of field, the wire would just melt. Instantly. Poof. So to solve this, engineers had to rely on a type of technology that honestly still feels like science fiction.
They turned to something called superconductors. These materials are just incredible. When you get them ridiculously cold, their electrical resistance just drops to zero, gone, which means you can pump truly enormous amounts of electricity through them to create a giant magnetic field, and they produce absolutely no heat. It's like a perfect, frictionless highway for electricity.
And when I say ridiculously cold, I am not kidding. These superconducting wires have to be bathed in liquid helium to keep them at minus 269 degrees Celsius. Let me say that again. Minus 269. That is just 4 degrees away from absolute zero, which is the coldest temperature that can possibly exist in the universe. That's what's happening inside that machine.
The material itself is pretty wild, too. It's a special alloy called niobium titanium. And get this, Our demand for medical scans is so high that a whopping 80% of all the niobium titanium that we produce on the entire planet is used for one thing: building MRI machines. That's just incredible.
Now, this created a whole other issue. Helium is a finite resource, right? And the early MRI machines were just constantly boiling off thousands of liters of this precious stuff straight into the air. Super wasteful, super expensive. But today's machines are way smarter. They're these engineering marvels called zero boil-off systems. They basically have a super powerful built-in refrigerator, think of it like a fridge on steroids, that catches the helium gas and cools it back down into a liquid, recycling it over and over again.
Okay, so we have our super-cooled, super-powerful magnet, and we're getting a signal back from the hydrogen atoms. Awesome. But that brings us to the next massive puzzle. How do you take that one single, jumbled signal coming from an entire slice of the body and turn it into a detailed picture?
This, to me, is the real magic trick of the MRI. The machine's receiver just hears one big, messy radio signal from millions of hydrogen atoms all chiming in at the same time. It's like trying to listen to an entire stadium full of people talking at once and then trying to figure out who is sitting where just from the sound. How does the machine possibly know which signal came from your brain and which came from, say, your nose?
The solution is just genius. It's something called gradient coils. Think of these as a second set of magnets, much weaker ones, that are laid on top of the main magnetic field. What they do is create a gentle slope in the field strength from head to toe. So now, the atoms in your head are in a slightly stronger field than the atoms in your feet. And because of that, every slice of your body now resonates at a slightly different frequency. It's like every part of you gets its own unique radio station. The MRI can then pick exactly which slice it wants to see just by tuning in to that slice's specific frequency.
Okay, but wait. That still only gives us one mixed-up signal from an entire slice. We still need to make a 2D picture out of it. To do that, the machine pulls out a trick that's actually over 200 years old, a brilliant mathematical idea called Fourier analysis.
So the basic idea here, and this is wild, is that you can create any picture you want, no matter how complex, just by adding together a bunch of simple black and white striped patterns. So the MRI uses its gradient coils to cleverly tweak the magnetic field in a way that organizes the signals into these different striped patterns. It then measures how strong the signal is for each stripe pattern. It does this over and over with different patterns, and then it uses that Fourier math to put all those pieces of the puzzle together and reconstruct the final detailed image. It's incredible.
And that noise, that awful, loud banging you hear when you're in the machine, well, now you know what it is. It's the sound of those gradient coils we just talked about being switched on and off hundreds of times every second. When you rapidly pass electricity through a coil inside a giant magnetic field, it creates a physical force that makes the coil vibrate violently. It's literally the exact same principle that makes a speaker cone move to create sound. You're inside a giant, very loud speaker.
And there's one last layer of genius here. Technicians can actually tune the machine to look for different things. They do this by listening to two slightly different properties of the signal called T1 and T2. You can think of it like this. T1 is about how quickly the atoms pop back into alignment. This turns out to be really good for getting clear pictures of fat. T2, on the other hand, is about how quickly the atom's signals fade away. And that's perfect for seeing things with a lot of water, like inflammation or certain tumors. So by playing with these settings, a doctor can highlight exactly the kind of tissue they need to see.
So the next time you see one of those black and white MRI scans, just remember what you're actually looking at. It is so much more than a picture. It's the result of this incredible, intricate dance between the quantum world of hydrogen atoms, the pure brute force of magnets cooled to near absolute zero, and the beautiful logic of math that's hundreds of years old. All of it working together perfectly, just to let us peek inside ourselves.
It is without a doubt one of the most sophisticated things humanity has ever built. And it really makes you think, doesn't it? If we were able to figure all of this out, mastering the invisible world of atoms to create these images, what other impossible things are out there just waiting for us to understand?